Okay, today we will talk about normal chi-square T and F distribution. And here are the definition for the four distribution. So we use letter Z, capital letter Z, to denote standard normal distribution, and with mean equal to 0 and variance equal to 1. So if we are given a more general normal distribution with some other mean and variance, we can always use that variables minus the mean and over its standard deviation, and then it will reduce to a standard normal distribution. And even given a standard normal distribution, we can also construct a more general distribution by say multiply by the standard deviation and then shift it by our specific mean, and then we can get or we can transfer from standard normal distribution to a more general normal distribution. And here, suppose we have an NIID copy of a standard normal distribution Z, and then denoted by I, and then if we take the square and then sum all of them together, that will give us the chi-square distribution. And then because we sum over n copies, and then that will that means we have that will be the degree of freedom for the chi-square distribution, where we use the subscript n here to denote its degree of freedom. And furthermore, if we have standard normal on the numerator, and then for the denominator we have this square root of a chi-square distribution with degree of freedom n, and then over its degree of freedom, and this thing together, this fraction here, will give us a t distribution with degree of freedom equal to n. Okay, and finally we have this one. So if we have a chi-square distribution that has a n1 degree of freedom, and then over its degrees of freedom on the numerator, and then same thing for another chi-square distribution with n2 degree of freedom, and then over its degree of freedom, and then this fraction here will give us F distribution, and then F distribution have a 2 degree of freedom, so it will denote that the first one is n1 and then the second one is n2. So all the subscript here is referring to the degree of freedom for its corresponding distribution here. And one important property or a rules for the construction of these distribution is that everything has to be IID. So this one, for example, everything has to be independent, and then if we take the sum, the square, and then the sum, it will give us a chi-square. Here, it also the numerator and the denominator has to be independent. Same thing here. So everything has to be independent, and then if we take the sum to construct the chi-square, and then, for example, this chi-square is also the sum, so everything has to be independent. And then if we take the sum to take the square and then take the division, and then that will give us the corresponding distribution here. So here are the four definition for these distribution here. And now we are going to go over some examples to show that how we can use this distribution to calculate the probabilities. Okay, suppose we have a variable x which follows a normal distribution, a general normal distribution with mean equal to 4 and sigma squared equal to 2. And now we are asked to find the value of c such that this probability is equal to 0.95. Okay, so we have two IID copy of a normal distribution, and now we are going to find the distribution of x1 minus x2. It will also be a normal distribution, and now we are going to calculate its mean and the variance. So the expectation of that, since they are IID, so we can the expectation of x1 minus x2 is expectation of x1 minus expectation of x2, and then we know that they all have the mean equal to 4, so the mean for x1 minus x2 will be equal to 0. And now we're going to calculate the variance of x1 minus x2. So since x1 and x2 are independent, and we can further expand its variance, so that the variance of x1 minus x2 will be variance of x1 plus variance of negative x2, since we can consider this as x1 plus negative x2. And then we have a minus 1 here. So if we move it outside to the outside the variance, it will have to take the square. So it will be a negative 1 to the power of to the power of 2, so that will become a positive 1. And then variance of x1 from here is 2. Variance of x2 is also a 2, so it will be 2 plus 2 will be 4. So that we know the distribution of x1 minus x2 follow a normal distribution with mean 0 and the variance equal to 4. From there, we can transfer this general normal distribution to a standard normal distribution by using that minus its mean and then over its standard deviation. So this will follow a standard normal distribution. And then we can apply the same procedure on the right hand side. So c minus 0 over the standard deviation. And then we can use a standard normal table to find the quantile for 0.95 and then furthermore to find the value of c from there. So yeah, here is just a demonstration by using the more general normal distribution, convert it to a standard normal distribution, and then find its probability or quantile. Okay, here we have another example. Okay, so yeah, so for say we have a random variable x that follow a normal distribution with mean 0 and 5. So that's a more general normal distribution, and then standardization will give us, say, x minus its mean and over the standard deviation. So x minus 0 over square root of 5 will be a standard normal distribution. Okay. So in the opposite direction, here we can also use starting from a standard normal distribution to construct the more general normal distribution. So we can just use z starting from standard normal multiplied by sigma and then plus its mean, and from a specific number here we have a square root of 5 multiplied by z plus 0 that will construct or give us back the normal distribution that x follows here. So that will be the construction in the two direction here. Okay, suppose here we are interested to find that the probability of this less than c is equal to 0.95. We want to find the value of c such that this probability holds. And now we are going to work on to find the distribution of the left hand side. Okay. So first of all, each of them are IID copy of the original normal distribution N05 here. And then we are going to transfer it into the expression by standard normal. So x1 from here can be constructed by square root of 5 times z. So the numerator here will be square root of 5 multiplied by one copy of standard normal distribution. Similar for the denominator. So because these are x squared, so we just do 5 squared, and then a copy of standard normal, and then take the square. So we have 5 multiplied by a square standard normal and its square. Okay. So now we are going to bring this square root of 5 outside, and then it will cancel out from the square root of 5 on the numerator, and then we are left with this term here. Okay, so from our definition of t distribution as well as chi-square distribution, here we will find out that 3 copy of IID standard normal, its square, will give us a chi-square distribution, and then with degree of freedom 3. And also we are going to multiply square root of 3 on both sides. So based on this specific or targeted construction here, we will have a chi-square distribution over with degree of freedom 3, and then over its degree of freedom 3 based on our targeted construction here. And finally, we on the left hand side, we will have a t distribution by the definition with degree of freedom 3. And then on the right hand side, we'll have a square root of 3 multiplied by c, and then this thing equal to 0.95. So from now on, we can use a t table, or you can use or some software to find that the quantile of t distribution to which that is equal to 0.95, and then furthermore find out the value of c. So from here, we use the standard normal distribution. Here we use the chi-square distribution, and then finally we use the t distribution, and then finally we can use a t-table to find the value of c for this equation to hold. Okay, here is another example. So suppose we have a random variable x which follow a normal distribution with mean 0 and sigma variance equal to sigma squared. And we want to find, say, a value of c such that this equation hold. Okay, so the numerator and the denominator has IID copy of normal distribution square. And similar to the previous example, we are going to rewrite that using standard normal distribution. So to construct x from standard normal will be sigma times copy of standard normal plus the mu, and then the mu is 0 here, so we can ignore all the mu's here. And then since they are all squared, so it will be sigma squared times z squared, and then same thing for all the x1, x2, x3, x4, and x5, and then we are up to, and then we will get this equation here, and then we can further cancel out the sigma from on the denominator and the numerator, and then so all the sigma is cancelled out, and then we are just left with standard normal square. And then we have 3 copy on the numerator, 2 copy on the denominator. And by the definition, the sum of the standard normal square, IID square, standard normal square, that will give us the chi-square distribution. So the numerator has a chi-square distribution with degree of freedom 3. The denominator has a chi-square distribution with degree of freedom equal to 2. So that's that. And now we are going to multiply 2 over 3 on both sides. And that will give us the numerator divided by 3, and then the denominator divided by 2. And then by definition, that will give us F distribution with degree of freedom 3 and 2. And then the right-hand side is still 2 over 3 multiplied by C. So now we can use F table to find the quantile for 0.95, and then we can finalize or we can further get the value of C from there. So we start from general normal to standard normal to chi-square, and then divided by its degree of freedom by the definition of a F distribution, get the F distribution. And then we can consult the table or using software to find the value of C. And okay, and here is our final example here. So again, we have random variable x follow normal distribution here, and then we are trying to find this one. The probability of this less than c is equal to 0.95. At the first glance, this might be very close to what we have in the previous example. However, the numerator and the denominator is both involving x2 and x3. So we have x2 and x3 here. So they are not, the numerator and the denominator are not independent. So we have to use some trick to make it independent first, and then we can use the definition of those distribution to construct, say, F or chi-square distribution. Otherwise, since they are not independent, they cannot be directly we cannot directly construct those distribution. Okay, so the problem is that we have x2, x3 on both denominator and numerator. Okay, so starting from there, first of all, let's change the sign. So we have, or actually to take the inverse. So we have x2 and x3 now on the denominator, x1, x2, x3 on the numerator, and then we also take the inverse on the right hand side, so it's 1 over c. But to do that, we need to flip the sign, so it's greater than, not less than anymore. So we take the inverse and flip the sign. Now we are going to push x2, x3 outside this fraction here. So we will have a copy of 1 plus this copy here. So the numerator is only left with x1 only. So we have 1 plus this copy here greater than 1 over c. And now we have make this copy here, or this term here, with numerator and denominator are independent. So now we push the 1 on the right hand side, so we have 1 over c minus 1. And this one is greater than that, so that the probability or still doesn't change anymore. And yeah, so now I just copy down this one here. And so now everything back to normal. We are going to use standard normal distribution to construct the x here. So sigma times z, and then we have to take the square. So sigma square, z square. And then same thing for the denominator. And then greater than 1 over c minus 1. So again, here we will have chi-square with degree of freedom 1 on the numerator, chi-square with degree of freedom 2 on the denominator, and then greater than that. Now we are going to multiply by 2 on both sides, and that will be equivalent to the numerator divided by 1, denominator divided by 2. So basically it's chi-square divided by its degree of freedom, chi-square divided by its degree of freedom. And then by definition, that will give us the F distribution with degree of freedom 1 and 2. And the right-hand side remain the same. And now we can refer to a F distribution, a table or a software, to find the quantile for the 0.95, and then we can find the value of C. Okay, so basically in this discussion, we are just kind of like manipulate by using the property or the rules of these distribution, and then to construct another distribution which we are more familiar with, and then we can find the probability or to find the quantile of that. So yeah, so here is the distribution, the definition of this distribution. And then one important rule is that everything, the numerator, denominator, or all the copies have to be IID in order to construct the corresponding normal chi-square T and F distribution there. Okay. Thank you very much.